So now we're on to section 9.4, which is acid catalyzed hydration. And here you see we react an alkene with water in the presence of sulfuric acid, and we get an alcohol. So here's a clicker question. What is the major product? That's this. Is it Markovnikov or anti-Markovnikov? Go ahead and pause the video and answer for yourself. So the OH added to the more substituted position and that is Markovnikov. So the correct answer is B. Now let's look at some relative rates. So if we just have ethene and we do acid catalyzed hydration on it, we get a primary alcohol. And the relative rate of this reaction is 1, whereas if we have 1 propene let's try this again. 1 propene. Really? And we do acid catalyzed hydration on it. It goes with a relative rate of 10 to the 6 to give us a secondary alcohol. That's 1,000,000 times faster. Jeez. Okay. So if we then have 2-methyl-1-propene, and we react it via acid catalyzed hydration, we get a tertiary alcohol with a relative rate of 10 to the 11th. That's a relative rate of 100 billion times faster. Way faster, right? So looking at that rate data, what can we say about the mechanism, i.e. what kind of intermediate is formed? And to answer that, since the fastest rate is what we get when we have tertiary product, we can be pretty sure that the mechanism has a carbocation intermediate, which is in fact true. So let's draw the mechanism for one of these reactions. So here's an alkene, and our first step is going to be proton transfer from the hydronium to the alkene. So here's our hydronium ion with its positive charge. And this gives us our carbocation intermediate, with a proton added to the right-hand carbon to give us the tertiary carbocation. That makes this go much faster. Okay. The next step is going to be nucleophilic attack by a water molecule. So here's a water molecule. And we're going to attack that carbocation. And this is going to give us a tertiary oxonium, a protonated alcohol. Okay. And then our third step, if we have another water molecule, it can act as a base. So that's the final proton transfer step to give us our neutral alcohol. So you can see this goes through a carbocation mechanism. This is step 1, proton transfer. Here's step 2, which is nucleophilic attack, and step 3, which is proton transfer. So that's acid catalyzed hydration for you. Now we're going to look at the thermodynamics of acid catalyzed hydration. So on the left-hand side, we will have our alkene and water. And if we do the addition reaction, our product will be tertiary alcohol. And the reverse, of course, is the elimination. So as far as delta H is concerned, the pi bond is weaker than sigma, which makes the addition product more stable. So delta H favors addition. Now, as far as delta S is concerned, we go from 2 particles to 1 particle. That makes delta S negative. That favors elimination. Right? And delta H favoring addition is a negative delta H as well. So, can we use temperature to control our outcome? Of course we can. Recall that delta G equals delta H minus T delta S, and a delta G less than 0, that is a negative delta G, is favorable. Right? So, at low temperature, delta H wins, delta G is less than 0, and we get the addition product. High temperature, delta S wins, delta G is greater than 0, we get the elimination product. So you can favor one product or the other by using an ice bath for addition or a hot water bath for elimination, respectively. Now you may be suspecting that temperature is not the only variable that we can manipulate to change the outcome. We can also manipulate the concentration of the H2SO4. So, if our reaction is alkene plus water yields alcohol, then our equilibrium constant is going to equal the concentration of the alcohol over the concentration of the alkene times the concentration of the water. If we increase the concentration of water, That gives us a reaction quotient less than our equilibrium constant. That shifts the equilibrium to the right. So you can accomplish this, a higher water concentration, by using dilute H2SO4. On the other hand, if you decrease the concentration of water, that gives you a reaction quotient greater than K, which shifts the equilibrium to the left. You accomplish this by using concentrated H2SO4. So dilute H2SO4 is going to give you the addition product. Concentrated H2SO4 will give you the elimination product. Thanks for watching.